Why does this fighter jet have a strange looking fin under its fuselage? And what does it have in common with this fighter jet or with this Airbus A340 and its strange wings? Well, today we're going to look at something called laminar flow and the ways that various projects have been exploring it. And we'll see why this is such a big deal for the future of aviation, but also why we haven't taken full advantage of it yet, even though we've known about laminar flow for decades. And we'll also see why this may be about to change thanks to NASA's latest project, because if it works, this technology could suddenly make our current generation of airliners almost obsolete overnight. That NASA aircraft with the fin below the fuselage is an F-15, testing the cross-flow attenuated natural laminar flow wing model, and it flew in this configuration for the first time on the 29th of January 2026. Now, for this to make sense, I need to explain what laminar flow is and how it differs from turbulent flow. And I know that their names sound self-explanatory, but things are a bit more complicated because sometimes we want laminar flow and sometimes we don't. Now, the best way to visualize the airflow over the wing is to look at a cross-section of the wing and imagine the air flowing over the upper surface as the aircraft flies in straight and level flight. As the air moves over the wing, the tiny molecules right next to the surface of the wing actually stick to the surface of the wing due to friction effects. And the molecules just above the surface are slowed down by the collisions with the molecules sticking to the surface. And these molecules in turn slow down the flow just above them, and so on. So the further away we move from the wing surface, the fewer the collisions affected by the air at the surface of the wing. And this small layer of air just above the wing is what we call the boundary layer. Now, when that airflow over the wing is nice and smooth, it's classified as laminar. And that slower layer of air wouldn't disturb the air immediately above it, which is a bit faster. And that layer wouldn't mix with the air above that, and so on. The layers would instead stack and flow past each other nice and smoothly, like the pages in a book or a stack of new playing cards sliding across a table. And this effect can be quantified by something called a Reynolds number, which expresses the ratio of the air's inertia, or its resistance to change, to its viscous forces, or how thick or gluey the air is. Low Reynolds numbers are good indicators of laminar flow, and high numbers normally indicate turbulent flow. If the airflow isn't laminar, which can happen when the wing cuts through the air at a large angle, or what we call a higher angle of attack, then the air layers above the wing surface would mix and swirl randomly, and the smoke mixed in the air would no longer remain smooth and well defined. Even when the wing is at a lower angle of attack, like in the cruise, the airflow could still be turbulent because of the shape of the wing or other factors such as the roughness of the wing surface. But the point here is that the laminar flow and the turbulent flow differ in two ways: drag and stability. When the layers of air above the wing are turbulent and interfere with each other, they generate what we call skin friction drag. And turbulent airflow generates about 2 or 3 times as much skin friction drag as laminar flow would generate in the same conditions. However, the air over the wing tends to become less laminar as it moves from the leading edge to the rear of the wing. And that's because the curve of the initial upper surface of the wing causes the air to accelerate, reducing the air's pressure. But then the upper surface straightens slightly, which creates a slight pressure rise. And if that pressure rises too steeply because of, say, a high angle of attack, then that laminar boundary layer of air can start rapidly separating from the wing, potentially causing a very sudden stall. By contrast, and this can be quite counterintuitive, mildly turbulent airflow, even though it's a bit more chaotic, is actually a lot more resistant to boundary layer separation. So mildly turbulent airflow can actually be preferable in some conditions, like when we're flying slowly or at higher angles of attack, due to its ability to remain attached to the wing for longer. Now, the whole topic of how wings generate lift is a complex one and is often misunderstood. And I'm not going to deep dive into the aerodynamics involved in this video. But what matters here is that the air over the wing initially accelerates, lowering the pressure, and then decelerates, increasing the pressure, which in turn can cause the laminar layers to start separating, which is worth remembering for later. And Based on this, if we could design a wing that manages to keep the airflow laminar for most of its surface, say 50 to 60% front to rear, then we could potentially reduce drag by around 10 to 15%. And that is a really big deal. To put that 10 to 15% into perspective, when Boeing and Airbus re-engined the 737 and A320 families, the gains they got from those new engines was around 10 to 12%. So imagine what it could mean to get that much more simply from an aircraft with laminar flow wings. However, there's a catch. As I said at the start, we've known about the benefits of laminar flow for decades. In fact, the first experiments on wings with laminar flow were conducted by NACA, the predecessor of NASA, back in the 1930s. And from all the way back then, people had two general approaches on how to design wings that took advantage of laminar flow. The first and simplest way was to come up with a wing aerofoil whose shape naturally made the airflow laminar, and predictably, this was called natural laminar flow. However, this was really difficult to achieve, especially given the lack of experience the industry generally had with aerodynamics at the time. Also, in practice, mass producing aircraft wings with no surface imperfections was pretty much impossible. The second way though was mechanical, a kind of brute force approach. And remember that boundary layer that I mentioned earlier that had slower moving air? Well, aircraft designers fitted test aircraft with a glove over a section of the wing, which had suction slots or tiny holes along its upper surface, and a vacuum pump would then suck air down through these holes. The purpose of this design was to get rid of that slow, turbulent boundary layer by literally sucking it through those tiny holes in the wing, so the air remaining over the wing would be the laminar, faster air, reducing friction considerably. This method was called active laminar flow control, and incredibly, the first testing of this technology was done back as early as the 1930s, although the design and precision of the era wasn't really good enough to prove the theory. Now, the Second World War stopped this kind of testing, and aircraft designers mostly switched their efforts to come up with better natural laminar flow or work with what they had. But the idea re-emerged after the war. NACA and later NASA would conduct both natural and active laminar flow testing on a variety of test aircraft in the decades that followed, all the way up to the 1990s. And perhaps the most iconic of those active laminar flow control aircraft came in the 1990s, when NASA had the technology to make really good use of that air suction method and gave us what was one of the most striking looking test aircraft ever flown, the NASA F-16XL-2, or ship number 2, modified for the supersonic laminar flow control experiment. Even unmodified, those F-16XLs look pretty radical, and we might revisit them in another video. But the two-seater variant that you see here in the picture had this strange black section on its left wing, and this area was part of a larger glove fitted over the plane's own left wing. And what makes this test pretty amazing was that this black area, which was made of titanium, actually had over 10 million tiny holes all cut using a laser. And it also had a pump that was fitted to the fuselage, which was connected to these tiny holes to suck the turbulent boundary layer away. This test was meant to provide data for use in the design of future supersonic airliners. And as a comparison, the right wing also had a glove for the same purpose, but this one was passive, i.e. it had no holes. During testing, there was an engineer sitting in the rear seat controlling the pump and monitoring the test results. And the test proved that eliminating the turbulent boundary layer was incredibly beneficial. But unfortunately, it also illustrated why you probably won't fly in an airliner using active laminar flow control anytime soon. Basically, it was too fragile. And I'll explain why after this.
In aviation, safety relies on meticulous checklists and time-tested procedures. If any of those steps aren't done properly or are missed, then the aircraft just doesn't get airborne. And without proper cash flow, your business can't get off the ground either. That's why professional invoices are so vital to getting paid in full and on time. Plus, they make you look like you know what you're doing, even if you're just starting out. And that's where today's sponsor, Odoo, comes in. Odoo is an all-in-one business management software designed to keep your business, well, flowing. Here, let me show you. With Odoo's invoicing app, creating an invoice takes seconds. Identify your customer, add the right products or services and quantities, and select your payment terms. Shoot it off by email and collect your payment by redirecting your customer to the customer portal where they can select their preferred payment method like Stripe or PayPal. You can see all of your invoices in one place with automated color-coded status updates for easy follow-up. Now, the first app is free for life, so you can start invoicing professionally today. But Odoo offers 45 different apps to support different business functions like sales, website, project management, and much more. Plus, you can bolt on extra apps as your business grows for an affordable subscription. And you can try your first app for free by clicking the link in the description below. Thanks, Odoo. Now, let's get back to the video.
The problem that the F-16XL and its incredibly complicated suction mechanisms had was something that had already been observed in previous testing with such setups: contamination. In aviation, we use the term contamination to describe anything that can cover the wings, tail, or fuselage of our aircraft and cause a degradation in lift or performance. And there's a real focus on wings because even a small amount of ice can dramatically reduce our stalling angle of attack, which is why we have anti-icing systems on board and de-icing procedures at airports. There's also performance degradation considerations that we need to consider with icing. For example, even if the wing is clean, any ice on the fuselage can introduce surface friction that generates extra drag. But when it comes to laminar flow, the materials that could cause contamination issues go way beyond ice. Imperfections that are just fractions of a millimeter can actually interfere with laminar flow. So insects or even rain or dust and water can adversely affect the performance. This issue was observed with natural laminar flow setups, but with active systems sucking air through tiny holes, the issue becomes even more complicated. And that's because even when it works perfectly, it has complex implications, particularly for airline ground crews during turnarounds. For example, think how much longer planes would need to stay on the ground if crews needed to inspect and clean the wings of any contamination from bug remnants and dust. The mechanisms itself possibly could be designed to shed water automatically, but what about a mix of water and dust or insect bits all mangled together? And even if every airline had armies of people maintaining and cleaning the boundary layer plumbing mechanisms overnight, how quickly would these systems get clogged again during the next day's flying? As a pilot, another issue we'd have to think about is fuel planning. Would we be able to accurately plan our fuel burn for a flight if we're relying on these systems to work in order to maintain laminar flow and its efficiency? These questions are probably why we haven't seen newer testing of active laminar flow control systems since the 1990s. Well, at least as far as we know. But let us know in the comments if we've missed something, and remember to hit like and subscribe while you're there. So, all of these complications are why more recent testing has focused on passive or natural laminar flow, which brings us nicely to this strange looking Airbus A340. This aircraft was used for the BLADE program, which stands for Breakthrough Laminar Aircraft Demonstrator in Europe. And even though it didn't involve pumping air through the wing, it was still a very complicated project. Unlike NASA and its project partners, Airbus didn't add a layer or glove over the existing wing. Instead, Airbus basically got rid of the outer wing sections of the A340-300 testbed and fitted new wing sections with the shape they wanted. And the reason the aircraft looks so odd is because the new test sections, which are around 10 meters long, have less sweep than the plane's normal wing. And Airbus did that deliberately because they wanted to test a laminar flow wing profile that's suitable for short to medium range airliners. In other words, a replacement for the A320 or the 737 families. These aircraft have less wing sweep than the A330 and most other wide bodies because smaller aircraft typically cruise at lower speeds. However, the sweep of the BLADE test section here is 20 degrees, which is actually a little bit less than the A320 and 737. And speaking of wing sweep, swept wings actually introduce another factor that can be a bit of a problem for natural laminar flow. And that's because of something called span-wise flow, which is basically a portion of air that travels laterally out from the wing root to the tip, instead of simply from the leading edge of the wing to the trailing edge. That conflict of air that wants to go from front to rear and air that wants to flow laterally is called crossflow, and it can end laminar flow prematurely. With the active laminar flow that NASA's F-16XL testbed was exploring, both of those flows would be tidied up or sucked into the wing and allow the airflow to remain laminar. But with natural laminar flow, the amount of sweep and other aspects of the wing's shape need to be just right in order to avoid these crossflow problems. And this is the technology that Airbus tested with its BLADE demonstrator. And as I already mentioned, this is a representative wing design, not only in terms of its shape and sweep, but also because it includes movable ailerons whose operation provides even more information to Airbus's engineers. The wing and the plane's surrounding structures are all fitted with cameras and other sensors that monitor the wing's performance at different speeds and altitudes. And some of these cameras were focused at painted lines on and near the wing. The cameras could also see the reflection of these lines on the wing itself, and they could spot any imperfections on these reflections, either from contamination or from the air forming a shockwave over the wing as it moved at transonic speeds. And believe it or not, that shockwave is something you can actually see on an aircraft wing if the sun hits the shockwave just right. Before the test, Airbus expected that this specific setup would reduce wing friction by 50% and overall drag reduction of 8%, which would translate to a reduction in fuel burn of around 4.5 to 5% on a typical 800-mile flight, compared to the wings we fly with today, which really is a big deal because fuel can be around 40% of an airliner's operating costs. But as it turned out, the actual results were even better. Overall drag reduction was as much as 10% instead of 8%, and Airbus found that airflow remained laminar even at higher speeds, at Mach 0.78 instead of the expected Mach 0.75. But then came the hard part though, understanding how this technology worked when the wing was contaminated. To do this, engineers added different kinds of imperfections, basically stickers with different surfaces and shapes. And in general, the results showed that contamination really mattered when it was placed forward on the wing, but actually had much less of an effect if it was moved towards the rear. And this kind of makes sense and was more or less what was expected. So if this technology finds practical applications, expect to see ground crew regularly cleaning the leading edges of the wings. So that's the BLADE program, which is a finished project and produced a decent amount of available information if you want to look further into it. But what is NASA's cross-flow attenuated natural laminar flow adding to this testing? Well, obviously NASA didn't replace a section of the F-15's wing to do its testing, but that fin underneath the aircraft's fuselage actually creates a few unique handling issues for the pilots. For one thing, this fin is not symmetrical. It's actually shaped like an aerofoil of an aircraft's wing, only it's sitting vertically instead of horizontally, which means it creates side loads and roll forces that the pilot has to counteract. Like the Airbus BLADE though, NASA's F-15 testbed will basically be used as a flying wind tunnel to gather data, but there are some notable differences. Firstly, this wing section is configured with a much higher wing sweep angle of around 35 degrees instead of the BLADE's 20 degrees. And that's because NASA sees this as a test for aircraft the size of a Boeing 777, not a 737 or an A320. The wing is therefore optimized for higher cruise speeds of around Mach 0.86. Secondly, NASA is a bit more ambitious. Instead of a fuel burn reduction of 4.5 to 5% that the BLADE project aimed for, NASA's project wants to validate fuel savings of up to 10%. So, how is NASA hoping to achieve this? Well, let's first remind ourselves that higher wing sweep angles can make it easier for span-wise flow to destabilize the boundary layer and stop the airflow from being laminar. So, before mounting this aerofoil on the F-15 testbed, NASA conducted extensive wind tunnel testing on aerofoil shapes. And remember what I said earlier about how the air pressure changes on the upper surface of the wing, increasing slightly towards the rear? Well, NASA has developed an aerofoil with a new geometry that keeps the pressure distribution more consistent. If it works, it should allow the airflow to remain laminar over about 56% of the upper surface of the wing. And if NASA hits that target, it would amount to a 7% drag reduction at Mach 0.86. Obviously, the placement of the test wing is limited in size to around 40 inches or just over a metre. And because it could apply asymmetric loads on the aircraft, NASA's test pilots carefully tested its behaviour during a series of high-speed taxi tests, which thankfully proved uneventful. For its very first flight, NASA's F-15 and its crew took off from Edwards Air Force Base and flew for around 75 minutes, confirming that the asymmetric fin under the aircraft's belly didn't give them any significant control issues. They flew their pre-brief manoeuvres at altitudes between 20,000 and 34,000 feet with no surprises. Unlike the BLADE A340 testbed, NASA's F-15 has cameras and other sensors mounted on pylons to provide data on the performance of the wing. Then, like Airbus and their partners did, NASA will test the behaviour of the wing when various stick-on contamination types are applied to it, and they're hoping that this aerofoil design won't give them any nasty surprises. Again, NASA's project is only just getting underway, so we're going to have to wait a bit to see how successful it is. And finally, it's worth remembering here that developing the perfect airfoil isn't the end of the story. The reason aircraft wings are so difficult to design and build is because they need to work very differently during different phases of flight. The lift that a wing generates at a constant angle of attack changes with airspeed. So lower airspeeds equal lower lift and vice versa. So in order to maintain the desired trajectory, the wing needs to be able to maintain the required lift at a wide range of airspeeds. And to achieve this, our wings have the ability to change shape with what we call high lift devices, flaps and slats that extend out and down to increase the curvature of the wing, which in turn increases the lift for a given airspeed. And this is absolutely crucial to enable our aircraft to fly slow enough to take off and land safely. However, in the cruise, all of these features effectively need to disappear. And that's because a highly curved wing that's great for slow flight is really no good for high speed flight. To fly at high speed, we want an aerofoil that's as smooth and efficient as possible. So all that complexity is irrelevant when we're in the cruise. All we care about up there is having a wing that's as slippery as possible, which is what these laminar flow projects are all about. But it's worth remembering here that the engineers who will eventually turn these aerofoils into real wings will still need to figure out how to get them to transform from draggy low-speed wings into super efficient high-speed ones. And this is exactly the battle of aerodynamics. Just when we solve one problem, another one crops up. But I don't think these problems are insurmountable, and it's definitely worth keeping an eye on as they progress. Anyway, I hope you've enjoyed this deep dive into this fascinating tech, and let us know in the comments below if there's any other similar developments that we should look into, or if there's anything else you'd like us to explain further. I'm Ben Watts, you're watching Mentor Now. Have an amazing week, and I'll see you next time.